Hello, this is Maxim Balmer, and today I will talk about our planet's inner workings and the sustainability of life on Earth. So this is a picture of a volcano in Japan and some wildlife and nice cherry blossoms. And in this talk, I will address the question how these pictures are connected, how these processes, basically life and geologic activity, which are also connected to volcanic hazard or general natural hazards, are connected to each other. So we're seeing here some intelligent life forms that are bathing in a hot spring with some also bacteria, I guess, within this hot spring, and a nice cherry tree. So basically, I will try to answer the question why the blue planet is a green planet. So here we see animation of the vegetative cycles and seasonal cycles on our planet. So the colors in the oceans are showing how the plankton thrives in the summer and then dies away again in the winter. I can fast forward here a little bit, so the globe will be turning and showing a bit more of the Pacific. But basically, we are seeing how life is shaping Earth and how basically the whole planet is alive and it looks like it's breathing with the seasonal cycles. So we understand how life works on our current planet. We also understand here in the top right how life evolved as the landscape changed throughout the geologic evolution of our planet. We understand less well how life originated on Earth. So basically going from amino acids and nucleobases to DNA or RNA, which makes up life and codes the information that is needed for evolution. So this step that goes from very simple molecules basically to this very complex double helix is fairly unknown. So I mean, this cannot just have happened by chance, that some molecules would have assembled in this complicated way, and some atoms, but there have to have been some specific processes and mechanisms that have allowed life, allowed amino acids basically to become life by allowing metabolism and multiplication through evolution. Then, as I mentioned, the processes that have led to slow and then much faster evolution in the Phanerozoic are much better resolved. So this big question, of course, is also connected to another maybe bigger question: is there life on other planets? So here at the bottom we see the inner solar system, which shows the terrestrial planets Mercury, Venus, Earth, and Mars. And at the top we see one of these exoplanetary systems that have been recently discovered, the so-called TRAPPIST-1 system, named after a Belgian beer. You know, that's what I guess scientists are thinking about day and night. And in this case, there have been 7 planets discovered which have a similar size as Earth and which might also be able to host liquid water at its surface. So this is the concept of the so-called habitable zone, here in green, where liquid water can survive, so that the surface temperature of these planets may be above freezing and below the boiling point of water. You will see here that the inner TRAPPIST system is enlarged by a factor of 25. So you might wonder why these planets that are actually very close to their host star are not boiling, basically, are not much hotter than the Earth. And that's because the star itself is much less bright and much less hot than our sun. So how do we know about this TRAPPIST system or other exoplanetary systems which have been discovered in the past? There are different methods to infer the properties of these exoplanets. One very successful method is the transit method, where the exoplanet circles around the host star, and then there are changes in the light curve of the star because the exoplanet transits in front of the star and also behind the star. Then you would get a slight minimum as well. Then also you could imagine, due to the gravitational pull between the planet and the star, that there would be a slight motion or wobbling of the star, which can be also in front of a background star, for example, which can be also observed. But all these methods are very indirect. We can't really directly observe very well the exoplanet itself, even though in the near future this might be possible with better telescopes and ongoing or planned missions. But for the moment, we can only have rough estimates on the planet's size or volume, and also on the planet's mass. So this gives us the density of the planet. But of course, there are trade-offs. I mean, if there, for example, a planet could be completely rocky, or it could have an icy envelope and a metal core, and that would be an ambiguity that is hard to resolve. But then from the temperature of the star, which you can estimate from the spectrum of the star, so the light spectrum, and the distance of between the star and the planet, which can be estimated from the time it takes for the planet to move around the star. So for example, for the time between these two minima here, so this would be in this plot time and intensity or brightness of the star. You can estimate the surface temperature of the planet. So basically, from the surface temperature of the star and the distance, you can have a rough estimate on the surface temperature. And if that's between freezing and boiling, then this might be an interesting planet to look at a bit further in the future. So that brings us back to the TRAPPIST system, why it's interesting. So these planets are, you know, from the criteria that we can robustly assess, they are Earth-like. They are rocky planets. They have a size and a mass that is similar to Earth, so presumably rocky. And they also have potentially liquid surface, liquid water at the surface. But the real question is, what are the preconditions for sustainable life? So is it really, if you just have temperatures between freezing and boiling, is that enough for life? If you really have, say, liquid water at the surface, presumably, I mean, hydrogen, oxygen are very common elements in the universe. So these kind of temperature estimates, does that already imply that there should be life, even though, of course, we don't know how much evolved that life is? Are we just talking about very basic life, or higher life? But what does this imply? I mean, really, what else should we think about or care about when we talk about the concept sustainability of life? And one problem that we face here is the so-called n=1 problem. So there is only one planet that we know about that hosts life. So we really don't know what the conditions for life are. Do the conditions have to be just right, just like on our planet, for life to originate and to evolve, and to be sustained over billions of years, to have the time to evolve? Or can you have different types of life forms, maybe not even carbon-based life, maybe I don't know, selenium-based life, or a silica-based life, silicon-based life, on very different planets? Or even when we talk about carbon-based life, do we think, for example, or is there life on the Jovian moon Europa, beneath the ice sheet of the Jovian moon Europa? If there is life there, if we will find out maybe in a couple of years or decades that there is life on Europa, that means that the conditions for life are probably not that specific. If there is really life, for example, in the clouds of Venus, as has been very recently suggested in one paper, that there are some bacterial life forms there, then maybe the conditions are not very specific. But for the moment, and for this talk, I will adopt the perspective of Earth-like conditions, and what are really the conditions here that allow the origination and evolution of life. So what me as a geologist and as a geoscientist, as a geophysicist, I think myself, what distinguishes Earth from other planets geologically? And we will see later on in this presentation that the interior processes of our planet are really crucial to sustain life-friendly conditions for billions of years. So this is just a video of what happens during an earthquake. We see a supermarket, everything is shaking. This is in Japan. So this is not the first time that the people witness a sizable earthquake. So you will see that the people, they walk immediately to the corridors and try to stop expensive sake from falling to the floor. Here, let's see. So here they're not very. So it's still shaking, but they're already doing their jobs. So very good, very good. So these are earthquakes. These are of course natural hazards, but we will also see that we should be happy that there are earthquakes and volcanism on Earth. So volcanism is the next video here. This is from the fissure eruption that finished off the Pu'o, the 30-year-long Pu'o eruption on the big island Kilauea volcano in Hawaii. This was the last big eruptive episode of this long-term eruption. So the geologic activity on Earth that we are facing at the surface is expressed through earthquakes and volcanism, and we are sometimes quite bothered with it, right? With a lot of fatalities and impact on our society. What causes earthquake and volcanic eruptions? So this is just showing a picture of the South Atlantic Ocean, and maybe you have already recognized. I have recognized this as a kid when I was looking at the map that the outline of South America neatly fits here into the outline of Africa. And other people have recognized this before. For example, this guy, Alfred Wegener, and he also recognized that if you looked at fossils, fossils from a couple of tens of millions of years back, on 1 or 100 million years ago or something, match quite well. So the fossil distribution, basically, the kind of fossils that you find in South America and in South Africa, they match with each other. And then he came up with the theory of continental drift, which at the time, in the 20s, or even I think just before the 20s of the last century, so more than 100 years ago now, was not very popular. Only a few people advocated it. But later on, there was more evidence for it. And okay, if I jump back a little bit, what you see here in the middle of the Atlantic is a so-called mid-Atlantic Ocean, a mid-Atlantic ridge, where the two plates, the African plate and the South American plate, are pushed apart from each other, so the Atlantic spreads there. And this is a mid-ocean ridge. This is one of the plate boundaries that we find on Earth and where a lot of volcanism occurs. So most volcanism on Earth really occurs at mid-ocean ridges, because two plates are pulled apart and then new material is sucked up and melts and forms new seafloor by very extensive melting, and the new seafloor then is basalt. So that's the same type of rock that you find on Hawaii everywhere. So that's a typical volcanic rock when Mantle so the Earth mantle material melts. And then, yeah, you know, these two plates in the South Atlantic are only spreading about 2 centimeters per year, but there is a continuously formed along this spreading axis a 7-kilometer thick, more or less, basaltic slab. So there's really a lot of volcanism going on there along plate boundaries in general, but mid-ocean ridges in particular. That's where most of the volcanism on our planet occurs, and that's how a mid-ocean ridge looks like exposed at the surface. So this is an image from Iceland, where the North Atlantic mid-ocean ridge is exposed at the surface, because this is a place where a hotspot, such as in Hawaii, so there's also a hotspot in Iceland, where a hotspot kind of overlaps with a mid-ocean ridge, and where therefore there's so much volcanism that it doesn't happen at the bottom of the sea, but it happens beneath air, basically. And we can walk along this big fissure, map it out, collect rocks, and have a look at it, have a look at these formations. And you can already imagine that this is a big kind of suture zone where two plates are pulled apart from each other. And this is how the theory of continental drift and plate tectonics gained more credibility by looking at these mid-ocean ridges, and in particular by looking at data from ship tracks. So if you go by ship across a mid-ocean ridge, so for example in the North Atlantic, and measure the magnetic field, and this is what happened in the 50s and 60s, then you will see these magnetic lineations, which are shown in the bottom plot. And these magnetic lineations are the expressions of shifts or reversals of the magnetic field. So the Earth has a magnetic field, and when new rocks are formed at the spreading axis, as I mentioned here, there's a basalt formed consistently, then the magnetic field is kind of printed into the rocks. And the rocks, so the seafloor spreads and new rocks are formed, and then there's a few million years later, there's a magnetic reversal. So the South Pole is at the North Pole, and the North Pole is at the South Pole, so to speak. And then there will be an inverse magnetic field locked into the magnetic rocks, so into the volcanic rocks, and that's how these lineations are formed. And these lineations are very consistently formed with the reversals of the magnetic field, and that lends us that gives us a lot of insight into the process of spreading, and basically shows that the spreading more or less continuously has been going on since 100 million years more or less in the North Atlantic, and 120 million years, I think, in the South Atlantic. Today we can even measure the plate velocities by GPS. So the theory of plate tectonics and of continental drift, which is, you know, one part of the plate tectonic theory, is directly confirmed. When there are these mid-Atlantic ridges and, well, mid-oceanic ridges, so in the Atlantic, in the Indian Ocean, and in the Pacific, where new plates are created, then there has to be also some other locations where plates are destroyed, basically. And that's where one plate is submerged beneath another plate, and that's called a subduction zone. So this happens, for example, in Chile, at the west coast of South America, but this also happens at the east coast of Japan. And this is a very famous example, because we also get strong earthquakes, because this subduction is happening, of course, in steps, in discrete steps. Subducting plate gets locked, the upper plate gets loaded, and then there's another earthquake. Happens only once in a while, because these motions are, as I mentioned, on the order of centimeters per year. Then a big earthquake only happens once in a while, but it does happen regularly. And in 2011, there was a big one in northern Japan, northwestern Japan, the so-called Big Tohoku earthquake. And you're familiar with the big tsunami that was formed due to the rebound of a riding plate when the earthquake was triggered, and all this energy was basically elastic energy was released, and that caused a huge tsunami and eventually destroyed Fukushima Daiichi nuclear power plant. So here on this graph, we just see the big earthquake, the big cycle, and many foreshocks and aftershocks or other earthquakes that happened in a given time frame in this region. So this is just a computer simulation of the workings of a subduction zone. So we see again that consistently one plate is submerged beneath the other. There's a so-called accretionary prism here in front. So there's a lot of geology that you can do there. In the back, there's a back arc basin, so a basin that forms, and there's sedimentation going on here. And there can be also melting in the mantle and volcanism. But the most important is that that plates are submerged and going down into the mantle. So at divergent plates boundaries, at spreading centers, plates are formed, and here plates are submerged. I just make another point here. I go a bit back here. So when you have two plates colliding and both are continental plates, then this submerging of plates is not that easy, and you will form a mountain belt. So this example is a computer simulation that simulates the formation of the Alps, where at the end here you will see that the subducting slab is peeling off, and then actually the Alps are rising, and you will get also erosion, of course, related to this rising of the mountains and mountain building. If I go back again to the previous simulation, sorry for jumping back and forth, but these are two oceanic plates in this case that are, one oceanic plate is submerged beneath another oceanic plate. I should have mentioned that. And this goes very smoothly and consistently because oceanic plates are thin. So here the oceanic crust is thin and it is dense, and it's easily submerged and then happily sinking into the mantle. Whereas the continents are more buoyant. They're mostly consisting of granites, which have a lower density than basalts. And the continental crust doesn't really want to become here. You see this continental crust here gets stuck here. It doesn't really want to go further down. These two continental plates at the top, they are colliding with each other and folding up this mountain belt. And then eventually there's necking of the subducting slab and dripping of this slab, which leads to uplift, as I mentioned, of the overriding plate. The important thing about plate tectonics is that you have these mid-ocean ridges, which are divergent plate boundaries in light blue, and you have these convergent plate boundaries or subduction zones where plates are basically consumed and going down into the mantle. Mid-ocean ridges, plates are formed. Subduction zones, plates are consumed. The important thing is that you have a mosaic of plate boundaries. So that that these plate boundaries basically connect with each other and define discrete plates. And these discrete plates, they don't show a lot of deformation internally, but most of the action is happening at the plate boundaries. So most of the volcanism, as I mentioned, is happening along the mid-ocean ridges, but a lot of volcanism also happening in the back arc between the arc and the back arc of the subduction zones. And then also as a third type of plate boundary, there are transform faults, and you might be familiar with the San Andreas fault up here, which are just connecting. So this is happening on a sphere, right? So there's no way you can have divergent plate boundaries and convergent plate boundaries everywhere. So at some places you have these transform faults or conservative plate boundaries, which are connecting them with each other and forming this mosaic, this plate tectonic mosaic on Earth. So what I will show next is an animation of of the seafloor spreading and continental drift. And you will see here the continents in black. You will recognize these outlines of the continents here: North America, South America, Greenland, Africa. And this is the present-day seafloor. And the colors will show the age of the seafloor. So I mentioned the magnetic stripes, right? And here you see that the age structure, for example, of the northern Atlantic. And oh, I have to correct myself. The northern Atlantic started spreading at about 120 years ago, here in these light blue colors, and the South Atlantic is a little bit younger, just about 100 million years old. But the youngest part of the seafloor is close to the mid-Atlantic ridge, where the age is basically 0. And I think these contours are in 10 million year steps. And the oldest part of the seafloor in the present day in the Atlantic side, is along the coasts of Africa and North America. But the oldest seafloor total worldwide is actually in the West Pacific. We can just not see it here, but we will now see an animation which, sorry, I will start it again, which starts about 200 million years ago. And here, this is actually the Pacific plate. So it starts as a small triangular plate, and this is the Izanagi and Farallon plate, and the Pacific plate grows at the expense of these plates. Now the Izanagi plate is subducted and gone. The Izanagi plate does not exist anymore on the present-day Earth, and here the Farallon plate is also starting to be subducted. And only a very small sliver of the Farallon plate, which is now called the Juan de Fuca plate, still exists on the present-day Earth. So this is the picture that we've just seen. And if I play the movie again, then you will see how the oceans spread. So the oceanic ridges open up and form new seafloor. The seafloor is consistently subducted along the subduction. This would be a subduction zone. And then India arrives, crashes into South Asia, and then the subduction zone doesn't continue anymore. It would peel off, as in the example for the Alps that I have shown. And now you see that also there's a very old seafloor in the East Mediterranean, a remnant of the Tethys Ocean. But I think, I'm not sure, the visualization here might be a little bit wrong, but because I think the oldest seafloor is actually in the West Pacific. So the next question is, what's driving plate tectonics? I mean, is this the hand of God moving around the continents and pushing the seafloor and forcing it down at a subduction zone? What's going on there? Mantle convection is driving plate tectonics. What is a mantle convection? Mantle convection is, the motion of the mantle. The mantle, of course, is rocky, but it still moves under the high pressures and temperatures in the deep interior of the Earth. So the mantle is this Earth sphere beneath the lithosphere. The lithosphere is the crust and also the lithospheric mantle, but that's just the rigid lid, basically the plates that are moving at the surface, and they are roughly 100 kilometers thick in old ocean basins, or maybe 200, 250 kilometers thick in very old continents. But the mantle goes down to a depth of 2,900 kilometers, so almost 3,000 kilometers or 2,000 miles beneath the seafloor. That's where the core mantle boundary is, and then the outer core is liquid, and the inner core is solid metal, basically. So back to mantle convection. So mantle convection to first order is thermal convection. So you have a hot core in the center, and the hot core is basically like a boiling plate. It's like if you put a pot of stew on a boiling plate, but this is just in spherical geometry. So the boiling plate is in the center, the hot core, And here in red, this would be hot, and blue, this would be cold. So these hot upwellings, or so-called plumes, are driven by instabilities of the core of the thermal boundary layer at the core mantle boundary. So this is basically like in a boiling pot of stew. It gets hot at the bottom, and then the stew rises, and you get convection. This is what convection is. Or if you look very carefully at your miso soup, then you can actually observe the little particles in the miso soup, and they are convecting. In a coffee, it's a bit more difficult to observe, but in coffee, you will, in the hot coffee can, you will see the same thing. And in the mantle, it also happens. And I will motivate you to visit this website, and then you can play around with mantle convection yourself. You would wonder why the mantle, which is a rock really, which consists of minerals, it behaves like a fluid on long time scales. I mean, we're talking again on these velocities of upwelling and downwelling, which look here very swiftly. They are just on the order of centimeters per year, or maybe maximum, a meter per year in the center of one of these hot upwellings or plumes close to the surface. So why does the mantle basically move without breaking? Why does it behave viscously instead of like a brittle? It behaves like a fluid because actually the atoms slide past each other. So this is a mechanism that goes very slowly, but it's fast enough to accommodate these convective velocities of centimeters per year. And this is a little bit like in a wire, right? A wire is solid, but you can still move it, right? It doesn't immediately break. It kind of flows, and that's exactly what happens in a metal, even at room temperature. So the metal also consists of crystals of iron or steel, and these iron atoms basically slide past each other, and that's how you can bend the wire. And very similarly, this kind of deformation process is happening in minerals in the interior of our planets, in rocky minerals. So this is another science visualization of mantle convection. It's a bit more sophisticated. So here now we have a viscous deformation and flowing of the mantle in the interior, but we also consider that the surface actually behaves plastically, so behaves like a brittle rock with fractures and so on. And the deformation at the surface is focused here, for example, at this subduction zone here, but also at some of these mid-Atlantic or mid-oceanic ridges, which are hard to see in this visualization of rock type. But we actually do get some kind of plate-tectonic behavior in this modeled planet, modeled 2D planet. So this is a computer simulation again. But you can see how, so red in this case would be basalt, and blue would be hardsburgite, which is another rock type. You will see how these subducted slabs are entrained into the mantle and mixed through the mantle. And some of this basaltic material actually accumulates at the bottom. I'm a bit sorry for this rotating back and forth. This is not so not so important right now. How do we actually know about this? How the Earth looks like in the interior? How do we know that these simulations are showing something reasonable? So how can we look into the Earth? And the way we do it is by earthquake waves. So if there is a big earthquake here, so I can go to the beginning again. So this would be the earthquake starts and sends earthquake waves through the entire planet, which at the surface, very close to the earthquake, would trigger ground deformation and maybe destruction of buildings and so on. Even though this particular earthquake is quite deep, so these very deep earthquakes, they usually don't cause a lot of destruction and hazard, but they travel through the entire Earth, and thereby basically scan the Earth. So if you have many of these earthquakes, ideally deep earthquakes, because they are very, very clean, they give very clean signals, and then these signals are recorded at multiple seismic stations. So say here in China there are a lot of seismic stations, here in Australia there are seismic stations, and of course also in North America. Even on the seafloor there are some seismic stations, even less than we would like. So these seismic stations record this earthquake. They record many earthquakes over the last 30, 50 years. And then when we take all this information, we can make a seismic tomography of the Earth. So we can really scan the Earth, like if you take a brain scan in the hospital using a computer tomography. This is a similar kind of mathematical approaches to tease out the information from all the seismic arrival times, or even the seismic waveforms that are recorded at the seismic stations. So then you can make a tomography model, and like if you look at a brain scan, you look at the different cross sections. Maybe you've seen that in the television before. Here you would see it. Here you would have a look at different cross sections through the Earth, and the colors here are showing velocity anomalies. So in these red regions, the earthquakes propagate slowly, and in the blue regions, the earthquake waves, so the sound waves triggered by the earthquake, are propagating relatively fast. And then this gives us an image of the interior. And here in Hawaii, indeed, we see one of these hot upwellings or mantle plumes. And now this explains why we have a hotspot there, right? So this material is rising up. It's actually also pushing up the seafloor, something that you can see around Hawaii, which is called the Hawaiian swell, and which is feeding the hotspot, and there is melting at the hotspot, partial melting of mantle rock, and these melts come up. And we've seen the eruption in the video before. And we see other of these plumes here beneath Iceland, for example, beneath St. Helena. And we also see subduction zones, right? For example, here there's one. This would be the slab that is subducted here near Peru, and then sinking into the lower mantle. Or there is another subducting slab here, which would be in Central America. So going the Pacific slab or the Coco slab, going down here beneath Central America. So this is showing that the type of mantle convection and also expression of plate tectonics that we've seen before, and that is a quite robust in observations. So different seismic tomography models from different research groups around the world are showing similar kind of structures, which are indeed reminding ourselves of these numerical simulations that we've just seen before. So the next question here, and I totally apologize for the German slide, but the next question is which energy source drives mantle convection? So of course, mantle convection drives plate tectonics, and well, they are intimately connected with each other. The sinking slabs, they also steer the mantle, so this is a give and take. But really, the energy source comes from the mantle. So the mantle is ultimately driving and shifting around the plates and the continents over millions of years and billions of years. Our Earth is 4.5 billion years old. So what is the ultimate energy source here? This is, on the one hand, is the decay of radioactive nuclides in the Earth mantle. So the mantle is heated from within, even though most of these radioactive nuclides, such as uranium, thorium, but also 40 potassium, which you might be familiar with from eating a lot of bananas, right? So there's a radioactive isotope of potassium. So these are in the mantle. Many of these isotopes are at the bottom of the mantle, but okay, we're heating the mantle from within due to the decay of radioactive nuclides. But also the core, as I mentioned, is very hot, and it's because the core still stores residual energy from the Earth accretion. And how is that? So here is just another one of these simulations, but then in this case, it's a simulation of two planets colliding with each other. And this is a model that might show a similar process as has happened in the very early days of the Earth, where if we go back to the beginning, this planet might be the proto-Earth, and this might be another small Mars-sized planet, which is called Theia. And Theia presumably collided with the Earth about 4.5 million years ago. So just, you know, at the beginning of our, not very, so maybe 50 or 70 million years after the, the beginning, the early days, the first days of our solar system. And this is just crashing obliquely into Earth and releasing a lot of energy here in yellow and white. And in the end, leaving a debris disk from which the moon, so this is the start of the debris disk here, from which the moon has formed. But then we also see a lot of this gray stuff here, for example, sinking down. So this gray stuff is metal, which is coming from the core of Theia, and which is sinking here to merge with, and here as well, to merge with the core of the proto-Earth and forming the Earth core, the last step of, this is the last step of Earth core formation. But previous giant impacts have happened to form this big proto-Earth in the first place. And during each of these giant impacts, a lot of metal is sinking down into the core, a lot of metal from the impactor, and this is releasing a lot of energy. So this is basically metal falling through through a molten, presumably magma ocean mantle, and releasing a lot of energy. I mean, it's like when a big rock falls through the air. So in this case, a big lump of metal falls through liquid rock, but it's the same thing. There's a lot of energy, potential energy release involved, and this energy ultimately is still stored in the core. The core starts off very, very hot, and then it's still hot, and it releases this energy as the inner core, the solid inner core, and in the present day grows at the expense of the liquid outer core. So this releases latent heat and heats the mantle from the bottom. So this is just, sorry for going back and forth, but this is just to explain, again, this bottom point where the residual energy, which is mostly driving mantle convection, is coming from. And yeah, so it's driving mantle convection, and it's driving also ultimately plate tectonics. But, you know, is this something special? I mean, does every planet exhibit plate tectonics or not? I mean, if every planet exhibits plate tectonics, then why am I talking about this in the context of, you know, life on Earth and life on other planets? I will say that Earth is the only planet so far we know about that hosts, that exhibits plate tectonics. And we can see the differences between various, you know, terrestrial objects in our solar system by looking at this histogram of topography. So the Earth has a bimodal distribution here, where this peak here is the, you know, the deep ocean basins, and this peak here is basically the continental platforms, such as North America or something, or Africa. Whereas if you look at Venus, it has a very different distribution. It doesn't have this two different types of plates. So in the Earth, these are basically the oceanic plates, and these are the continental plates. On Mars, we do have a broad distribution. And maybe in the very early days of Mars, there was an ocean in the northern hemisphere and a continent in the southern hemisphere, but there was never really a plate tectonic mosaic so a mosaic of plate boundaries that would support plate tectonics. And the moon also doesn't show something like that. If we just zoom in a little bit on our sister planet, so Venus really is our sister planet. It's also, you know, in the habitable zone in a way, even though it's at the edge of the habitable zone. In principle, it might host, so if it had a different atmosphere, it would be able to host liquid water. But Venus has a very dense atmosphere and a very strong greenhouse effect with, with a very high pressure at the base of the atmosphere. I think several hundred bars instead of just 1 bar on Earth, and a very high partial pressure of CO2. And even though Venus does have some blocks that almost look like continents, and there is some discussion about whether these are actually granitic blocks, at least in some regions, so-called terrae, here and there. And they also have some structures which could be incipient subduction zones. Some scientists believe that this structure over here is an incipient subduction zone, and also all these so-called coronae are related to plume activity, which is related to mantle convection. There definitely is a vigorous mantle convection on Venus, but there is maybe even some subduction, but there is not a plate mosaic. We don't see a widespread, we don't see any geological evidence here in this detailed topographic map of tectonic structures, maybe except for, very limited ones that support a plate tectonic mosaic. This might be a rudimentary form of plate tectonics. Some people call it soft lid behavior, or plutonic squishy lid, or something like that. Different terms have been proposed for this. And maybe in the early Earth, so in the first 2 billion years of the Earth history, in the Archean, for example, the tectonic activity of the Earth might have been similar when the Earth was still hotter than today, might have been similar than on Venus today. But we don't really know, to be honest. Just to compare, a plate tectonics planet such as the Earth with a stagnant lid planet such as Mars, or maybe Venus. As I mentioned, there's some debate about what's going on Venus. But a stagnant lid basically means no tectonic activity at the surface. And that's what we really believe is at least present day Mars. So it's kind of boring, dead. If you want as a single plate that does not move, of course, it's just one plate, it's global. Whereas on Earth, you have on a plate tectonic planet, you have a plate mosaic with subduction zones, mid-ocean ridges. You have a lot of volcanism at mid-ocean ridges, quite a bit of volcanism at subduction zones, and then also some volcanism at hotspots. And on so-called stagnant lid planets such as Mars, you would only have limited volcanism at hotspots. But these hotspots could be stationary. And such as on Mars, there might have been a hotspot beneath Olympus Mons, a huge volcano on Mars, for billions of years. And then these hotspots might actually form large volcanoes. I mean, Olympus Mons is the largest volcano in our solar system. But yeah, these are significant differences in the dynamics, the interior workings of plate tectonic and stagnant lid planets. And we will see later that this has important implications for global scale cycles, for example, volatile cycles. Here, these cycles are just, separated from the surface through the thick stagnant lid. This is another science visualization, this time of a 3D model, 3D numerical model of mantle convection beneath the stagnant lid. So we see these plumes, but we don't see any subduction zones. So the lid here is continuous. Nothing basically happens. There are upwellings and downwellings, but there are no really subduction zones where lithosphere is submerged and recycled into the mantle. Instead, on Earth, we do have plate tectonics. We do have subduction zones which accommodate plate tectonics. We do have mid-ocean ridges, and we do have life. I mean, maybe it's just coincidence, but there is life on Earth. There is plate tectonics on Earth. Earth is the only planet we know of that hosts life. Earth is the only planet that we know of that hosts plate tectonics. But why would plate tectonics be important for life? So why would there be a connection between the two? Why wouldn't it be just a coincidence? So one important thing is, I already mentioned it, are these global scale cycles. So these global scale cycles of CO2 and H2O, which are both greenhouse gases, right? Are so the basically sediments on the ocean floor are subducted into the mantle, and these sediments host carbonates. They host hydrous sediments, right? Minerals that have water in their atomic structures, and all this is submerged into the mantle and then stored in the mantle. Actually, the mantle probably hosts 2 or 3 oceans, or at least 1 ocean. I mean, there are different opinions about that, but there is a big reservoir of CO2, which is probably 100,000 times larger than the surface reservoir of CO2 in the Earth mantle. So, for example, a lot of graphite and diamond in the Earth mantle. And this is, of course, a big buffering reservoir, right? You have continuous fluxes going into the mantle and also coming out of the mantle at mid-ocean ridges and hotspots. You know, volcanism, of course, there's water and also CO2 and sulfur, other things coming out of the mantle again. But this is also going down again. So there's this huge cycle, and thereby the volatile reservoirs at the surface are buffered. And indeed, for example, the volume of the oceans on the Earth has not varied too much in the last hundreds of millions of years, as far as we know. And also, ultimately, the level of CO2 on the surface is buffered this way. Unfortunately, the timescales of this buffering are, of course, much longer than human timescales. We can't really hope on this mechanism to save us from global warming, but these are important mechanisms to sustain life-friendly conditions, or even just, you know, temperatures between freezing and boiling more or less over billions of years, even though the activity of the sun, for example, has changed. The sun has been less hot in the beginning of Earth evolution and has become more and more hot. So this is a faint young sun theory. But these kind of large-scale cycles have been able to still buffer the conditions at the surface for several billions of years on our planet. And on smaller, shorter time scales, there's another feedback mechanism that buffers the surface conditions, which is related to erosion and weathering. So I showed before these science visualizations of, you know, subduction and collision of continents and mountain building, right? So we are on a planet that has mountains, that has oceans, that has a lot of topography. And then we have also a little bit of an atmosphere, but actually most, as I mentioned, most of these volatiles which are in the atmosphere are actually in the mantle, and we would have a much more massive atmosphere without subduction and without plate tectonics. But yeah, this atmosphere is, of course, you know, there's rain and there's precipitation, there's erosion, and so the hotter it is, right? Say there's a temperature anomaly, for example, global warming, temperatures go up, or after an ice age, temperatures go up. More CO2 will be dissolved in rainwater, so we have sour rain. And there will be more erosion, also because, you know, global warming, more storms, more rain, more floods, and so on, more erosion. And erosion leads to weathering. So this means that you have silicates which are weathered, such as quartz, or, you know, from the weathering of continents, basically granites in the mountains that are weathered. And then these minerals are reacting with the atmosphere and with water, with rainwater, for example, acid rain, and are forming carbonates, but are also forming sheet silicates, which are incorporating a lot of water. So basically, due to this weathering, so basically I'm talking about clay, so sheet silicates is clay, another word for clay. This weathering draws down water, but also CO2 out of out of the hydrosphere and out of the atmosphere. And ultimately, it will be buried into the oceans and then even subducted into the mantle and be part of the deep mantle carbon cycle. And this removal of CO2 from the atmosphere, which is most effective at high temperatures, draws down the temperatures again, right? So this is a negative feedback due to erosion and weathering. When the temperatures get too high, they will go down again. Unfortunately, this happens on timescales of about 1 million years, and this will again not help us very soon with the human-made climate crisis, global warming. But eventually, in 1 million years at the latest, this will be balanced, and this is also helping us out of an ice age or out of a greenhouse situation. So in an ice age, you would have a low precipitation rate, less CO2 is removed from the atmosphere, and more greenhouse gases are in the atmosphere because they're continuously, of course, erupted at volcanic centers. In contrast, in Venus, for Venus, it doesn't work like that. Venus doesn't have plate tectonics, doesn't have surface water and precipitation to draw down CO2, but most importantly, it doesn't have plate tectonics, and then ends up in a runaway greenhouse. So most of, maybe not most, but much more than for Earth here in comparison, which, well, I made it a bit smaller, but these two planets are very similar size, right? So in Venus, much of the CO2 that is normally stored in the mantle is, exhausted from the mantle and eventually erupted at volcanoes into the atmosphere. Over time, it just ends up in the atmosphere. There's not a very efficient mechanism for CO2 to return from the atmosphere down into the mantle again, into the Venusian mantle, whereas for Earth we have plate tectonics and recycling related to plate tectonics and subduction. But for Venus we don't have that. So and this is called a runaway greenhouse, where just the temperatures would get hotter and hotter. So you have a greenhouse that releases more CO2 into the atmosphere, and then it gets hotter and hotter and hotter. And so it gets hotter. So that well, the way to explain it, sorry, is you have a greenhouse. You boil some water or evaporate water into the atmosphere. So and then water is also a greenhouse gas, and the greenhouse gets stronger, and you boil more. So you evaporate more water and gets hotter and gets. So this is the positive feedback, which causes a runaway greenhouse on Venus or presumably other planets. But Earth has avoided this fate because of what I just mentioned, the negative feedback related to silicate weathering, and also the long-term carbon cycle and water cycle related to plate tectonics and subduction. Another nice thing about plate tectonics and mantle convection is that mantle convection, so convection in the mantle, which takes out the heat from the core, as I mentioned, triggers convection in the outer core. The outer core is liquid. Here you see this in this cartoon. So there's vigorous convection of the outer core because heat is flowing out of the outer core and so, through the mantle by convection, and eventually lost to the surface. And this heat is powering a geodynamo. And in this case, it is a huge magnetic field, the so-called geodynamo, and it shields the Earth from the solar wind, from these highly energetic particles, which are guided around the Earth by the magnetic field, and therefore, at least land-based life is protected from the solar wind. So this allows land-based life, higher life, and even technology sustained civilizations such as the human civilization. So this is just to wrap up. Plate tectonics is indeed important of life, and the underlying mechanism is mantle convection, which is powered from the core, and then drives plate tectonics, and then you have volcanism, which puts CO2 back into the atmosphere, but also subduction, which removes carbonates and removes water, also recycles water into the mantle, and then the whole big mantle buffers CO2 and water reservoirs on the surface. So that brings us back to the question: is there life on other worlds? And I can't really answer this question here, I think, but I would argue that it translates to the question: is there plate tectonics on other worlds or on exoplanets? So we should think about whether these planets, for example, in the TRAPPIST system, can sustain plate tectonics. Of course, also, I will not say that plate tectonics is really required for life. We don't know this yet, but at the moment, the only life we know of and the sustainability of this life, and which allows the long-term evolution of this life on our planet, has benefited a lot from plate tectonics. Let's put it in this way. So if we want to look for good candidates, so if we want to spend a lot of time and money to observe an exoplanet very closely, maybe we would like to choose an exoplanet that has a high likelihood to host a plate tectonics. Which parameters would we look for to know if there's plate tectonics on an exoplanet? At the moment, this is not really well understood, but with new observations, maybe, for example, looking at the atmospheres of exoplanets. In the near future, we'll have direct observations from these atmospheres. And for example, we could distinguish a Venus-like atmosphere, I think, from an Earth-like atmosphere quite well. So that would be an interesting thing to look for. And yeah, just to wrap up this presentation, I would like to come back to basically to the first slide that I showed and highlight the connection between these three different pictures, and not just that all these three different pictures are taken from Japan. It's also that these three different, that life and geologic activity, such as volcanic eruptions on our planet, are intimately related to each other. So I hope I convinced you that at least the long-term sustainability of life, so sustaining life-friendly conditions on our planet for billions of years, which has allowed the evolution of these beautiful plants and these intelligent mammals, has been strongly sustained, and maybe only possible because we have plate tectonics on our planet, and plate tectonics is responsible for a lot of natural hazards, but we should be happy, I think, that plate tectonics is the way our planet works.